So thank you all for being here for the second talk by Dr. Hall. Going to continue with origami, and so Dr. Hall, please take it away.
Thanks. So this second half of the talk, I was told to do more math than the first one, so get ready. And as promised, there will be some linear algebra in this. But also, I'm hoping this will tie into the first talk because the math described here, all of it is very applied. Everything you see in this talk totally comes from me and my collaborators trying to answer questions that, well, we thought were interesting mathematically, but also arose from things, literal questions that physicists and engineers were asking us about how do we do this. And that should become apparent. But that's where the no hands part of the folding comes in. So let me explain a little bit about what you're seeing on the screen here. This is origami, folding and unfolding, but as you can see, it's not real, it's computer generated. It's a simulation of what's called rigid origami. So that is, there's clearly a crease pattern that is folding and unfolding here, but it's done rigidly, meaning that the polygons of paper, the faces of the crease pattern between the regions of paper between the creases are staying flat and planar as it's folding and unfolding. As if you were folding it out of sheet metal. That's where the word rigid comes from. Each panel of the crease pattern is staying rigid as it folds and unfolds. The only thing changing here is the creases. That each crease has what's called a folding angle, some angle by which it's folding, and they're all being folded together so that it's simulating what like a piece of paper or some structure folding and unfolding without ripping or whatever. But as you can see, it self-intersects near the extreme points here. When it folds all the way, you can see the polygons collapsing on top of each other. That doesn't actually happen with real materials, but this simulation was done in Mathematica, and Mathematica doesn't care. It's just like, I'll draw whatever you want me to draw. So you can see them like intersecting here as those panels come together. In reality, they would bump into each other there. But still, so I want to explain a little bit about how this kind of simulation is made. Although there's a lot of math there. There's actually too much math there for me to talk about. But then I want to address this question of if we wanted to, say, put this specific object into outer space and have it fold and unfold like this, how would we do that? Literally, how would we do that? That's a question that comes from the engineering community. Like how would we do that? In all the ways. Like, what would we physically have to do? How would we have to get the math to work for it to fold up like this and not in some other weird way that this crease pattern might want to fold into? Okay, so this all comes from matrix algebra for this, and it actually makes sense that this. So here I have a little tiny crease pattern here. This is a degree 5 vertex. I'm not indicating which creases are mountains and valleys there necessarily, but notice each crease has a number attached to it in radians. That's the folding angle. It's saying that the crease in the north position and the east and the west position, those all have to fold up to like a 90 degree angle. So here a folding angle means if a folding angle is 0, then there's no folding. It's like this. So the folding angle is how much the paper deviates from a flat state. If the folding angle is positive, it's making me a valley crease. Okay? If it's negative, it's making me a mountain crease. So that gives us, we could describe folding angles with a dihedral angle, the angle between the planes, but the folding angle, which is like I think technically the supplementary angle of the dihedral angle, is a little bit more natural, because then 0 means not folded, positive means valley, negative means mountain. And the furthest you could fold something is 180 degrees, or pi. So the south crease there has a folding angle of pi. That means that one is a full valley crease folding all the way. And the diagonal crease there is negative pi. That's a full folded mountain crease folding all the way it can. The others are 90 degrees, and if you fold this, you get this little 3D corner of a cube thing. That's that, okay? Now, but what you can do is describe this, or if you wanted to, say, simulate this on a computer, Mathematica, you would want to use matrices like the one down there. I don't know if, how many people are familiar with that kind of matrix. This is a three-dimensional rotation matrix. The cosine theta, negative sine theta, cosine theta, that 2 by 2 chunk of that matrix, that's a standard matrix that you may have seen before. It will rotate the xy plane. If I just take that little 2 by 2 thing out and ignore the rest, that 2 by 2 matrix, if you multiply that by a vector xy, it'll rotate xy about the origin counterclockwise by theta. And so if you augment it with this row of 1, 0, 0 and the column of 1, 0, 0, then what that's doing is that's rotating three-dimensional space. But if you imagine multiplying this by a vector x, y, z, the x coordinate won't change, right? Because you do 1, 0, 0 times x, y, z, and you get x times 0 plus 0 plus 0. So you just get x back. The x coordinate won't change, but the y and the z coordinates will rotate. So this three-dimensional matrix will rotate about the x-axis by an angle of theta. And so if I want to simulate this type of origami thingy, then I could literally, or the way I like to do it is I imagine holding one of those faces fixed. Usually I go with the one right under the x-axis, like this one. Imagine I take this face down here in quadrant 4, or whatever, and I'm fixing that. And then I want to rotate the other panels of the crease pattern by whatever folding angle I want. So that one right above the x-axis, I just got to rotate. To put that into place, I'm going to rotate about the x-axis by pi over 2. Okay. For the other one, well, you got to do something a little bit more complicated. But the idea is that all I'm going to do is use rotation matrices like that one. But in order for the paper not to rip, I gotta know what folding angles I need to rotate all of these creases by. Otherwise, I may do a rotation, 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 and all of a sudden they're not lining up again. Well, it turns out this equation is what allows that to work. So what is this equation? This equation is a matrix equation. Each element of this is one of those 3 by 3 matrices. So I'm using the notation where I want R of Li rho I. Okay, so Li, I'm labeling the creases L1, L2, L3, whatever. Okay, and R of Li rho I is the 3 by 3 rotation matrix that will rotate about the line Li going through the origin by angle rho I. Okay, so that's just one matrix like this, but it might be more complicated because I'm not necessarily rotating just by the x-axis. I'm rotating by about the y-axis, or this L4 diagonal axis, or something like that. Okay, but if I want the paper to not rip, then what I want to do is take all of those rotation matrices and multiply them together, and I should get the identity. The idea being there that if I was, this isn't quite right, but it's good enough. If I imagine going along this red curve that I drew, and suppose I was an ant, and I was walking along the paper as it was being folded, then I might be like, okay, first I'm going to, I hit crease, I don't know, L1, and I rotate about that. Then I hit crease L2, I rotate about that. I hit crease L3, I rotate about that. When I come back to the beginning, I should be exactly where I started, in which case the total of those transformations should be the identity. I shouldn't have, if I've gone somewhere else, if I didn't get the identity here, that means the paper is ripped or something like that. That's the basic idea. I'm brushing some details over, okay? But if you think about this, this is a matrix equation, okay? I could multiply all those matrices together, and you know what these matrices look like. They look like things like, except they don't because, I think I need to click. Oh, no, there we go. They look like things like this. They're going to have those folding angles in them, and they're going to have a bunch of sines and cosines in various places. So if I multiply all these together, I'm going to have a 3 by 3 matrix with a whole bunch of sines and cosines involving these folding angles, row 1, row 2, row 3, row 4. And it's got to equal the identity. So the upper left-hand entry of that matrix multiplication is going to equal 1. The first row, second column entry is going to equal 0. This gives me 9 equations involving trig formulas and the folding angles. And that's the relationship that the folding angles have to have with one another for this to not rip. Okay, so this one equation gives me everything I need, except it's easier said than done because some of these equations are messy. Yeah. So that's where Mathematica helps. You plug something like this into Mathematica and you say, simplify. And if you're lucky, something good happens. If you're not so lucky, you just got a god-awful trig formula, with all sorts of things. But you can get it to work, okay? And so I and other people have used this to make all sorts of animations of things folding and unfolding, like these animations down here of 3 different types of folding. That first one is called an augmented square twist. Although there I'm using the fun of Mathematica to have the paper pass through itself. Like paper won't do that, but what the hell, it's Mathematica. The one in the middle is kind of like the first one we saw at the beginning of this talk. It's very similar. This other one is part of something called a hyperbolic paraboloid, but there I was just having fun and making it be pretty colors. Okay, so all of these were made by equations like this, okay, and they can get kind of yucky, but computers don't care that much, and so it's humans care about yucky equations, not computers, not so much. Okay, so I want to describe where this kind of thing goes, what we can do with it, and for that we need a few more notations here. Okay, so there's something we call the configuration space. Whenever physicists love configuration spaces, so do engineers, and so do certain types of math fields like algebraic topology and algebraic geometry and stuff. And I like them in origami too because it gives us a way to visualize what's going on with some of these things. Okay, so I want to think if I have a crease pattern and I'm rigidly folding it. Okay, in fact, I probably have. Oh, I have some manipulatives I can use here. Like so, yeah. Here's a vertex. I'm folding and unfolding it. This is a degree 4 vertex. Okay, so there are 4 crease lines. As I fold and unfold this, each crease line has a folding angle, all right? And there's a relationship between them that's going to be governed by this matrix equation, okay? So what I want to do is, at each folded state, I want to look at all the folding angles, all 4 of them, and consider that a point in 4-dimensional space, okay? Where the x-coordinate is row 1, the y-coordinate is row 2, the z-coordinate is row 3, and the whatever w-coordinate in 4D space is row 4, the 4th folding angle. So then as I fold and unfold this, that will trace out some curve in 4-dimensional space. That's what we call the configuration space. It's literally a curve or manifold. It really depends on how many degrees of freedom you have on these things. But it's some surface, either a curve or a surface or something, some manifold in n-dimensional space if you have n creases in your crease pattern. Because crease patterns can be complicated, like in the previous slide that we saw. Okay? Yeah. So that's what a configuration space is. It's really just a way of drawing a picture of what your folding angles are doing, and it's visualizing their relationship. Okay? Now, sometimes we can get really nice equations for these configuration spaces. And this is one example. So here I'm applying this to a flat foldable degree 4 vertex. That's what I'm holding in my hand here. Flat foldable means, that's what I mentioned this in the last talk. Flat foldable means I can fold it all the way flat. Okay, I can press it in a book without crumpling if all the creases, in other words, all the folding angles can go to either pi or minus pi. Okay, so degree 4 means that there's only 4 creases coming out of the vertex. And we're just looking at, can we describe the folding angle relationships here? Here, it turns out, if you play with this matrix equation enough, you get some incredibly nice equations. Although, usually when I show these to people, they're not so impressed. I want you to be impressed. Okay, look at this. Okay, well, actually, let me show an animation first. Yeah, this animation. This is such a degree 4 vertex folding and unfolding. And here I'm actually showing the folding angles at the same time. For some reason, I called them phi instead of rho here, but whatever. Okay, so check this out. This is something you can observe using some other techniques too, or by just playing with one of these models in your hands. but it's a little hard to see. Human beings aren't very good at looking at things in 3 dimensions and being like, oh, this angle is blah. You know, we're just not trained for that, I guess. But if you let the computer tell you, notice what's happening here. As I fold and unfold this, so here I'll just keep it in this, let's keep it in like this state so you can kind of see what's going on. Yeah, so check it out. The creases are labeled phi 1, phi 2, phi 3, phi 4, just going along, I think, going along clockwise around here. And notice that in this way I'm folding it, I have 3 mountains, 1 valley, right? Phi 2 is the valley, and all the others are mountains. But notice some of these are equal, right? Phi 2 and phi 4, no, that's not right. 1 and 3 are equal. Yeah, I'm getting hung up by the negative signs. Yeah, phi 1 and phi 3, and those are the ones opposite each other. They're the mountain creases that are opposite each other. They're like these two here. You know, those are actually have the same folding angle as it's folding and unfolding. Like, let me move it a little bit in case you don't believe me. Like, maybe I just picked exactly the right spot. But if I fold it some more, you still have that same thing happening. Phi 1 and phi 3 are exactly the same. And phi 2 and phi 4 are also the same, except that one's a mountain and the other's a valley. So this is kind of remarkable that in this case, you get this situation where the opposite, you have a degree 4 flat foldable vertex. The opposite creases have the same folding angle as it folds and unfolds, except that 2 of them are going to be the same, like 2 mountains. The other 2 are going to be opposite. So one's a mountain, the other's a valley. So one will be positive, the other will be negative. And so that's what you're seeing down in the second row. Okay, so that's kind of cool. And that's actually not that hard to prove, except it uses something, well, the best proof I know of uses something called spherical geometry. Yeah, which spherical geometry is really cool. Yeah, but I don't want to talk about that too much, but just to give you an idea, imagine I put my degree 4 vertex at the center of a sphere of radius 1. And then I see how does the paper cut into the sphere. Then I get a spherical polygon. My paper cuts out a spherical polygon. And the folding angles are like supplements of the angles, the interior angles of that spherical polygon. So you can totally use the geometry of polygons on the sphere to prove this. It's actually kind of cool. But that would be like, I don't know, that'd be like a half-an-hour proof right there if we were going to do it. So I don't want to. So that's what we see happening here, okay? Degree 4, flat foldable vertex. I've labeled the angles between the creases, alpha, beta, and then pi minus alpha, pi minus beta. Oh, God, I didn't describe that either. Okay, that looks a little weird, okay? But this is another thing that always happens. If it's flat foldable, and I label, say, 2 of the angles between the creases. These are sector angles between the creases. One of them is alpha, the other is beta. Then the other 2 have to, because it all goes flat, the other pair of angles have to be like 180 minus this angle and 180 minus that. That's so that as it folds, again, it's almost like the proof we saw last time of Mayakowa's theorem. It's zigzagging back and forth. So again, if you kind of think of these angles as like being in radians and being these arc lengths, so you're like going along one arc length and another in the opposite, then another, and then you come back to where you started. So the alternating sum of these sector angles has to add up to 0. But at the same time, they all add up to 360, and that means these have to be supplementary and those have to be supplementary. That is just geometry of the fact that it can fold flat. Okay, so the picture has to look like that, like this disk that I drew here. Okay, and here on the side, I'm mentioning that if it's folding like this, the opposite folding angles are equal, except that one of them is positive, one of them is a positive negative pair. So here I've wrote that as rho 1 equals negative rho 3, and rho 2 equals rho 4. Those are the folding angles of the creases L1, L2, L3, L4. So L4 and L2 have to have the same folding angle as it folds, okay? And L3 and L1 have the same folding angle, but different sign. The tricky thing is how does, say, L1 and L2 relate to each other? Like, how do those numbers relate? Well, this is how they relate, which looks weird. You take tangent of rho 1 over 2 equals blah times tangent of rho 2 over 2. And I have grown to love this equation because, well, I hope it becomes a little bit clearer later. But check this out. Okay, this cosine over cosine business. That's cosine of alpha plus beta over 2, cosine of alpha minus beta over 2. Alpha and beta are these two angles. Those don't change as I open and close this. That's just like the angle between the creases on the paper, and they're not changing as I do this. So this puppy right here, this cosine over cosine, that's a constant. It's just a constant. So this is almost like a linear equation, except I got this tangent of the folding angle over 2 business. But if I think of this as almost like a way to reparameterize the folding angles, then this is like this folding angle equals a constant times that folding angle. That's like a linear equation. That's actually kind of remarkable. That's a much better relationship than we often get for these kinds of things. But it comes out of the fact that it's degree 4 and flat foldable. Okay, but there's more. This isn't the only way to fold this vertex. Okay, so here, if I orient my paper like this, this is me, folding it like that. Okay, in other words, I have a mountain crease here and the others are valleys. I could have swapped, especially around here I have alpha being the smallest angle between the creases. I could have made the other side of alpha be the lone mountain crease. And that's what we see down here. That's what I call mode 2. Okay, so these are that would be me not folding it like this, but instead folding it like that. Okay, it's literally a different way to fold it. All I'm doing is changing the mountain valley assignment, really. Okay, but they do have different equations. They're still the folding angle equations. They're still very similar to one another. Notice it changes like the opposite pair sides of the creases that are opposite each other. They still have the same folding angle, except now the mountain crease is moved. And I have a slightly different relationship between rho 1 and rho 2. It's still tangent of the half angles, and the cosines have changed to sines. So there's a little bit of a difference there. Okay, but still not so bad. Okay, so this is just like, ooh, these equations, I could use them to draw the configuration space, to draw the curve that tells me how, as I fold this physical thing that I'm folding, I can think of as a point on a curve that's traveling along over time. Like as time goes by and I fold this, then I'm traveling along a point on this curve, which we'll see pictures of in a little bit. So there it is again. Okay, yeah. So anyway. Yes, and so here's these types, so I can draw these things. Now again, because the opposite folding angles are equal, if I want to make a curve just to visualize it, all I really need to do is compare L1, like rho 1 and rho 2. But here I'm going to compare rho 1 and rho 4, since rho 4 is the same as rho 2. But those are, at least they stay in both mode 1 and mode 2, they stay valleys, the way I have it drawn here. So that's what I did here. I had rho 1 being the y-axis here and rho 4 being the x-axis. I could have swapped them. It wouldn't have made that much of a difference. But then we get these kind of curves. Okay, and notice, it makes sense. They intersect at the origin, right? Because the origin is this state. And that's how I could switch from one to another. That's what engineers get very upset about. They don't like the origin because it's a singularity of these curves. It's a place where if I'm an engineer and I'm trying to design an origami structure that is supposed to fold and unfold in outer space, and I want it to suppose I fold it to some flat state, and you put it in on top of a rocket or something that shoots off into outer space, and then it unfolds, and it's supposed to maybe fold into some configuration like this. I want it to maybe stay in mode 1, not accidentally go to mode 2. And the origin is where it could make a mistake and go along mode 2, and now my solar panel array doesn't look like it should, or isn't going to catch the rays of the sun like it should. Okay, so yeah. So what do we do about that? Well, this is where this thing called self-folding comes into play. This is the thing I mentioned earlier about how do we, if we're an engineer and we wanted to actually make a complicated origami crease pattern fold in a specific way, how would we literally do that? Well, this is a cartoon that kind of gets the idea across, although usually people come up with things more fancy than this, but you could just put springs on all the creases. I mean, this is one thing you could do. And actually, I have some models, like I'm going to show things like this. Like you put springs on the creases, okay? So this is made out of wood and there are springs, and we'll talk about that in a second. But then how would you get this to work? I mean, springs have some force, right? Springs have various strengths. One nice thing about springs is that if you just I don't know, go to a hardware store and buy a bunch of springs like that. These are called torsion springs. They're not springs that are meant to be bent like this. They're meant to bend. That's why they have these long arms, and they're like torsion springs. They give you torque. But if you buy a bag of these things, they're all the same size, and they all have the same force. At least you hope, because manufacturing error, who knows. But if you put the same spring on each crease, then each crease is trying to fold in exactly the same speed, exactly the same way. That'd be great if all the folding angles were the same, but we just saw that they're not. So no. But if you make a spring longer, that increases its force in a linear way. So what happens when we actually try to do this? So if I wanted to make my degree 4 vertex, if I wanted to make just something simple like this, fold and unfold along mode 1 and not accidentally go to mode 2, I would need to figure out what length of springs do I need to put on here relative to one another. And those equations we just saw totally help us do this, okay? But before we get to that, what you would literally be doing is if you think of your configuration space again as a curve, this collection of springs, each spring is a vector, or as a coordinate. Each spring gives you a force to put on the folding angle of each coordinate. You get a vector field, okay? If I go back and look at pictures like this, now this isn't exactly right, because this is only a 2-dimensional image, this degree 4 vertex. Its configuration space is in 4 dimensions, okay? So this is it projected down into 2. But you can kind of imagine, like if I was along mode 1 and I had some springs on each of the creases, it's going to push me in some direction. There's going to be some vector, some arrow, and you can imagine that like there'll be benches of arrows depending on where we are. And so imagine you just have a vector field over this. That's basically what's happening, okay? So the big question is, can we find spring strengths for the creases that will get us to some target state that the engineers want us to have this fold to, like maybe right here, or maybe all the way folded flat. Who knows? Okay, that's the big question. How do we do that? Okay, so and in particular, how do we avoid singularities? So that's what this slide is. Like if we want to figure out what springs are going to push us in the right direction and get us to the right state we want to go to, we want well, this is simplifying things a little bit again, but we want 2 basic things. We want the springs to push us in the right direction for one thing. But then when we get to any singular points, like at the origin, we don't want to go down the wrong path. So here's one simple way of getting around that. If we could, again, if we think of our springs as being a vector field, then we'll have all these vectors as we go along, and the springs are trying to push us in some direction. If when we get to the origin, and suppose we want to stay on this mode 1 curve, this desired folding mode, this desired path, if we get to the origin, if my driving force vector is perpendicular to the tangent of any undesired folding paths, then it's not going to go down the wrong path, right? Because that'd be like saying, hey, I want to go in this direction, and the bad directions are perpendicular to me. I'm not going to accidentally go, oh, the force is going to push me not in whatever non-perpendicular direction is. Okay, so yeah, so how do we quantify that mathematically? Well, if you know stuff about vectors, this actually isn't that hard. To go along, if I want to push, say, along this desired folding path, I want the angle of my driving force vector, my vector field, to make an acute angle with the tangent of my desired path, right? If it was making that obtuse angle, it might be sending me in the wrong direction, you know? Or if it was a perpendicular angle, it might not move at all. It might be just stuck there, you know? But if it's making an acute angle, it should still push me. Maybe not, it'd be great if it actually lined up with the tangent vector, but that might be too much to ask. If it's making an acute angle, it'll keep pushing me there. You can test that by taking the dot product of those two vectors, the driving force and the tangent vector. And if you get a positive dot product, that means you have an acute angle. Dot products are fun. I like them. Okay? But you, at the origin, you want your dot product with the mode 2 tangent vector, which I'm calling Q here. You, at the origin, so I'm plugging in 0 for the folding angles, you want that dot product to be 0 with the blue path. So these are things we can test. Yeah. And so I have a bunch of slides where we do that. And they're yucky. So please, you know, well, they're equations. You get equations. Okay, so like here's the mode 1 curve for degree 4 vertex. Okay, so this one, this is literally the one I have in my hands here. This is 45 degrees, 90, 135, 90. And if you plug that into this cosine over cosine thing, you get this, which isn't so bad, actually. Yeah. And then if you wanted to actually plot that on Mathematica, well, again, this is a 2-dimensional image. And actually, this isn't quite right. I think this is still a cartoon, but we'll see. Yeah, I think it's more symmetric than that. But if I was going to plot it out as a 4-dimensional point, which is what I need to do if I really want to test it out or study the math, then I would have, I'd have to do something like this. Like here I'm saying let rho 1 be t. Okay, because you get tired of writing row 1 and row 2 and row 3 a bunch. So let parameterize it with t. So that means the x-coordinate and the z-coordinate become t. T and t. But then the others are governed by this formula. So you solve for row 4, you take the arctan of both sides, you multiply by 2, and you get this garbage, okay? So yay, arctan, woo, arctan. Yeah. And then you plot that, and if I just plot row 1 and row 4, I get something like this. Well, except this is just mode 1. So I don't have the equation for mode 2 yet. But then, okay, so what's my driving force, though? Okay, so that's what this is supposed to describe. Like, what vector should I be pushing things if I want to, say, fold from one point of mode 1 to another point of mode 1? So I call rho of capital T my target. This is what I want to self-fold to. Okay, so I'll just pick some point on the mode 1 curve, maybe over here. It might be the all the way folded state, which would be this upper corner here. Then I'm claiming that a reasonable driving force would be this. Take the target point on my configuration space and subtract from it wherever else I am on the mode 1 curve, or anywhere, actually. Rho of t, wherever I happen to be in my folded state. And the reason why that's reasonable is, if you think about it, if I program my springs to want to be in, say, this position, then when I open them up, it's going to create tension. Okay, I actually have a model of this. This is something my students made. Here there are springs, okay, and this is the state it wants to be at, okay. And if I open that up, I don't know if you can hear this, but if I open that up, it creates tension. And the more I fold it, the more tension there is. It gets, you know, because I'm making these torsion springs go like even more against where they want to be. So by subtracting one point from another, if I'm really far away, I'm going to have a big force. Where if I'm close by, I'll have a smaller force. That's really modeling what the springs are doing. They're going to have a little force. If I'm really close to the target space, this is going to be, the vector force is not going to be very big, right? It'll be close. It'll be like there to there. You know, but if I really twist it around, it's like, oh yeah, what the hell are you doing, Tom? You can feel it. So by taking the difference of these vectors, that models what the springs are doing. The further away you are, the not so good it is. Yeah, so this is what I want a dot product with a derivative of this. And I want to get something positive for that first condition. Because that means that if I'm down here, this is going to push me along which according to this picture looks like entirely reasonable. Like, why wouldn't it do that? But remember, this isn't the real picture. The real picture is 4-dimensional. This is 2-dimensional. This could lie. Don't believe 2 dimensions, at least not here. Okay, so yeah, so we want to test this first condition. Is the driving force vector dotted with the derivative of the mode 1 curve positive? Okay, well, there's the mode 1 curve. There's the driving force. There's the derivative of the mode 1 curve, which I only got by putting this in Mathematica and telling Mathematica to take the derivative and telling it to simplify it. It actually comes out to something not so bad. But remember, the derivative of arctan of x is 1 over 1 plus x squared. This is kind of, yeah, derivatives. Yay, you can actually use them. Right. And then if you dot, so what do I have here? Oh yeah, so if you dot product that with the driving force, you get some crazy things. Because the driving force has capital T in it, that's my target state, and lowercase t in it, that's wherever I happen to be. And there's some stuff in here. But look at this. If capital T is bigger than lowercase t, which is what I have in this picture, then this part in the front, capital T minus lowercase t, that'll be positive. Okay? And arctan and tangent are increasing functions. So if I plug in something bigger into arctan and tan and subtract something smaller into arctan and tan, I'm going to get something positive. So this is always positive, as long as I'm kind of going in this direction, which makes sense. If I wanted to do it the other way, I would be taking the opposite of the tan. I'd have to introduce some negative signs anyway. So this actually works. The picture isn't actually lying. Even in 4 dimensions, the angle between my driving force vector and my tangent vector is acute. So it will push along in the right direction. But what about the other thing? Here, this is another cartoon. I want to take my driving force vector, the purple thing, and dot product it with the tangent of the mode 2 vector at the origin. I want those to be 0. This is a much potentially harder thing to act, because how do I know that's going to be 0? It doesn't, in fact, in this picture, it doesn't look like it would be, right? 0 means perpendicular. Those don't look perpendicular, but remember, this is 2 dimensions, not 4 dimensions. Don't believe the lies. Okay, so here I'm calling sigma of t the mode 2 curve. That's what that is. It's very similar looking to the mode 1 curve, but actually, this is the mode 2 curve down here. Instead of root 2 minus 1, you have root 2 plus 1. Okay, but again, that came from those equations from before. So what do we want to do now? I got to take the derivative of that. Yeah, so if you take the derivative of this and you plug in t equals 0, you actually get this. That's not so bad. But again, you're plugging in 0, so that basically makes some of the that cosine stuff turn to 1. So yeah, but then I gotta dot that with the driving force vector at the origin. That's this. Okay, so all the little t's go away because they're all 0 now, but with the capital T's. And if you look at this dot product is 0. It makes sense if you stare at it, because look, you got capital T dotted with 1. So you just get, so remember, dot product, you're multiplying the x and y coordinates together and then adding them all up. That's the dot product. That's all it's doing. So t times 1 is t, but then I have a minus 1 times the third coordinate here is another t, so the t and the minus t there will cancel. Woo! And then here I have root 2 minus 1, root 2 minus 1, and I multiply them with these arctans, but they're actually the same. Actually, I think there's a typo here. What'd you say? But yeah, this minus sign will make those cancel. No, there is a typo. I think these are supposed to be pluses. But whatever, it doesn't matter. Whatever they are, these are the same, except for this minus sign, so they will cancel as well. So everything goes away. Everything cancels out. That's great. Yeah, so in theory, this works. But what spring strength should we use? So the idea is that, okay, that driving force that we came up with is literally like what the spring should do. It was just following the physics of what springs do when you open them up. But it's also reliant on these equations, okay? So So what do we do? Well, okay, so these pictures are more accurate. Here we're taking advantage of the fact of what I said before, that if we reparameterize by tangent of half the folding angle, it linearizes these curves. If I just plot row 1 and row 4, these are the actual curves they get. That this is not a cartoon. That's what they really look like if I project into the row 1, row 4 plane. But if I instead I let the x and y axis be the tangent of half the folding angle, I get these lines. It's the slopes of these lines I want to be my spring ratios, okay? I want the slopes of that linearization because they give us the relative folding speeds that I want, and that corresponds to the strength of the springs. So if you look at these slopes, it's literally these numbers, root 2 minus 1 and root 2 plus 1, that are giving me those slopes. Again, because that's like these equations being linear. All right. So if I wanted to fold along mode 1, I want my folding speed ratios to be 1 to root 2 minus 1. And root 2 minus 1 is what? Root 2 is 1.414, blah, 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 blah. So root 2 minus 1 is 0.414. Do I have that on the next slide? Not quite. Or maybe I do. No, I do. There. So let me go back to here. So what that means is that for this, ideally, I would want the, let's see how this works. Yeah, I would want the pair that are mountain and valley opposite each other to be 1. No, that's not right. I'd want the ratio between the mountain-valley pair and the valley-valley pair to be 1 to 0.414. Now, again, because my students bought a bag of torsion springs, they didn't have a way to cut one into 0.414 of the length of the others. So what they did instead is they just doubled it. They said, oh, 0.5 is close to 0.414. And so they're using a ratio of 2 to 1. Okay, so that's kind of like, or 1 to 1/2, which is close, okay? But it actually ends up working pretty well. So there's a little bit of error induced here. So this is it folding into mode 1. And if I like fold it backwards, it will totally go into the right spot. And if I try to fold it into mode 2, now this is a little bit interesting because at first the students were very depressed. They're like, oh, it doesn't work. It's staying in mode 2. But that, you know why? Gravity. Gravity is kind of keeping it there. If I fold it all the way and do this, it does go into mode 1. Okay, so this driving force actually works quite well. And yeah, so people can play with this afterwards if you want. It's kind of weird. I mean, it's not that exciting. It's like all it does is this. But you can like twist it into mode 2, and it really will spring back into mode 1. But if there's too much like things weighing down on it, then the tension of the springs and gravity is like resisting what it really wants to do. If you literally get rid of gravity, it works just fine. So, good enough for outer space. All right. Yeah, so this is a picture. Okay, so I should watch the time. Oh, no, we're doing good, I think. This is a picture that shows the mode 1 and mode 2 folding speeds in a slightly different way. Here, I'm letting P be root 2 minus 1, and what this means, this equation down here means, there's a lot of neat things that you can learn from this that made the engineers really pleased, because what these folding speeds literally tell you is which pairs of creases are folding faster than the others. In this case, it says that the 2 pair that have the same mountain-valley assignment, so that the 2 that are both valleys opposite each other, those are going to fold faster than the valley-mountain opposite pair. And you can totally see that in one of these models, even in this paper model, that as I start from the unfolded state and start folding it, the 2 opposite valleys here, they reach 90 degrees way faster than the others. So like the others are still like making this kind of like obtuse angle there, whereas these 2 now are at right angles. And so, yeah, the opposite pair, they fold faster. And how much faster? Well, it's this number P, that's root 2 minus 1. That's how much faster. Whereas in mode 2, kind of the opposite thing is happening. Here, if I let the opposite pair, again, which is the same creases over here, if I let those be 1, now these two are folding faster. And that's because here, this multiplier, Q, is root 2 plus 1. That's bigger than 1, right? In fact, root 2 plus 1 is like 2.414. So these creases are folding faster. But those numbers P and Q are what are kind of what we get from this. So let me quickly mention what happens when we try to expand this to instead of just one vertex, 2 vertices. Because let's face it, not many engineers want to send this into outer space. They want to send big things like the mirror map fold and stuff like that. So what if I had 2 vertices? OK, well, it turns out that this doesn't work so well. And I want to try to explain to you how. Because if you have 2 vertices, then you have 4 combinations of mode 1 and mode 2 that you could do. You could have both. I think the top one here is both creases being mode 1. This one is both creases being mode 2. This is a mixture of mode 1 there and mode 2 there and mode 1 there, and then mode 1 there and mode 2 there. Okay. And I got this picture from a paper I wrote with, so this self-folding stuff is work I did with this Japanese guy, Tomohiro Tachi. And I stole this from our paper. And so here we kind of normalized the mode 2 thing so that they were being expressed as a number less than 1. But don't worry about that so much. So these are the 4 ways it could fold, okay? And I'm going to express the folding speeds in a matrix. Each row of this matrix is one of these 4 different cases. Each column is the creases. So here I've numbered the creases. The middle one is number 1, and then number 2, 3, 4, 5, 6, 7. I've just chose to order them that way. So in mode 1, I have the folding speeds are this top row. Okay, where those P's and Q's are given by those equations that we saw before, with those cosine over cosine or sine over sine things. All right, so this, if you actually take that matrix and you ask, if I were to try to row reduce this, it turns out to have rank 3. Only 3 of these rows are linearly independent. If you row reduce it, you can eliminate one of the rows. And that's bad. That's not good for self-folding. Let me explain to you why. Suppose that one of those rows was self-foldable. What if I could find some springs to put on the hinges to make it always fold, say, to that top one? Suppose I could do that. Okay? Well, then that means that whatever driving force gives me that mode 1 curve must avoid these other 2 curves, or these other 3 curves in the configuration space. So whatever driving force that is, I must be able to dot product with the other rows of this matrix and get 0. That way, at the origin, it's avoiding all these other 3 ways it could fold. But this matrix has rank 3. Whatever row, so suppose I could self-fold for the top row. That top row is a linear combination of the other rows, because this matrix only has to rank 3, right? So that means that whatever row that was, which I'm calling V here, can be written as a linear combination of the others. So when I dot D with that row, V, and then I substitute V with its linear combinations of the other 3 rows, which I'm calling V1, V2, V3, each one of them is supposed to have dot product 0. So I'll have also dot product 0 with D. That meant, no, I wasn't even pushing along the V curve. So the linear algebra doesn't work for this. There's kind of too much you have to keep track of in terms of the dimension of this configuration space. So you can't do what we did here. You can't do that with this. Not as simply as this. Okay. But other things do work reasonably nicely. This is something, I mentioned this before, this is something called the square twist. That's what I have here. And all this is like 4 of these vertices put together. But since they're making a loop, there's not just 2 vertices next to each other, it's making a loop, it actually introduces some other constraints. So this isn't perfect. This doesn't always self-fold to the right thing, but it often does. If I were to do this and throw it up in the air, it actually works pretty well. But I'm pretty sure there's some state, like here, where it doesn't. So there's some states it doesn't, but Others, like if I really try to twist it around, it actually works just fine. But there are a few places where I can reverse some of the creases but not others, and then have enough of the creases here are kind of doing what they want to do. That's what the linear algebra is actually kind of illustrating, that if you have too many creases that are like perfectly happy doing what they're doing, then the other ones that are unhappy aren't strong enough to force the happy ones to be unhappy temporarily to get to the flat state and go back. So if I just like twist one of these things, then yeah, even if I get rid of the gravity thing, it doesn't spring back into what it should. So this is super interesting. Yeah, I just have a few more things to show, I think, that are fun. Yeah, one last example. What about non-degree 4 vertices? Oh my gosh. Okay, so this is a case that actually works quite well and weirdly, all right? So this is a degree 6 vertex. I have an example here. This is a degree 6 vertex. And I don't know why I made this so big, probably because I knew I was going to be on stage. Look, degree 6 vertex. There's lots of ways to fold this. This has more degrees of freedom than a degree 4 vertex. But as you can see, the paper's getting a little floppy here, so you do have to be a little careful. But so this is work I did with this guy, Tomohiro Tachi. And we were like, how would we, if we wanted to, I don't know, self-fold this degree 6 vertex into this state that we call a tripod, okay? It's got alternating mountain, valley going around it. The tricky thing here is that even with this mountain-valley assignment, mountain-valley, there's more than one way I could fold it. I could fold it with this vertex popping up like this, or do I have, or I could pop it down, okay? So even if I have a driving force of just mountain, valley, like so, mountain springs, valley springs, mountain springs, valley springs, that would not distinguish this state from this state, where I have the same mountain valleys as I had before, but now the vertex is popping down instead of popping up. So we were like, how would we control for that? It turns out we can, though, if we do the same analysis. So here's another picture of these two pop-up states. I mean, I could literally, there are different modes. I could like switch all the mountains and valleys. Yeah, so there's actually a lot to keep track of here. But if you do the same kind of analysis, if you say like, well, in this case, all we really did was we said, let's keep track of what happens at the origin. First of all, we were able to come for this kind of symmetric folding, we were able to get the configuration space curves. That's what this diagram is showing. And it's just showing, since it's symmetric, we're just showing like row 1 and row 2, like just 2 of them. But we were like, okay, let's make it avoid the mode 2 curve here by having it be perpendicular. And the driving force vector that we would need to do that had to be something proportional to this. And we were like, wait, what? I don't know if you can see what's weird about this. If this is my driving force, okay, this is telling me the ratio of what the springs should do. I have 1 here, and I have 2 plus root 3. Yeah, 2 plus root 3. Those are both positive numbers. They're both valley creases. The math here is saying, I don't want springs to go mountain, valley, mountain, valley. I want them all to be mountains, or all to be valleys, but some of them to be a lot stronger than the others. That works. Okay, so I have a video for this, I think. Yeah, let's see if I can show this. This is my hand over something Tomohiro made. It's the same thing, but as you see, I will torque it, and it still goes back to that pop-up state. And Tomohiro is a mechanical engineer. He got springs to be very accurately what those those things were. Yeah. So that actually we were very surprised that this worked, that this case worked, whereas some of these other things don't work. And then I had some students of mine work on a similar degree. This is still the same degree 6 vertex, but now it's being folded into this bow tie configuration. That's this. So now it's like mountain, mountain, valley, mountain, mountain, valley. Okay, my students here called this the bow tie, and that ended up having they were drawn to this because it ended up having a really simple configuration space curve. I mean, like what, you know? So we did some math, and they made, again, they actually made friends with engineering students because my university has an engineering college, and the engineers were like, oh, let's totally do this. So they made this out of plexiglass, and it was really pretty. And it actually works quite well. And in fact, I think I have a video of Megan and Hannah illustrating this, so you should be able to hear this. Let's see how well this works.
So this is a rigid origami, degree 6 vertex with spring hinges that make a driving force.
Which is a vector field on the configuration space of the rigid folding.
To self-fold this into a bow tie shape.
Like this.
So we made this like over a year ago. The springs have gotten a little looser, but I think I can still simulate what Hannah did there. Yeah, it isn't quite as snappy, but so this has its problems. There's more degrees of freedom here than the degree 4 thing, but it actually works quite well, at least in a lot of situations. And I'm not even throwing it up in the air to get rid of gravity. What they then did is they wanted to tessellate this. So here's Taryn showing us. Open it up. Yep.
Like this way?
Yeah. Now close it. Dude. Yeah. So let me actually back that up because she didn't throw it up in the area. So this isn't quite complete. They actually made this a little bit bigger. But this is, they wanted to combine multiple degree 6 vertices in this bow tie configuration. But in order to tessellate them, they had to introduce some degree 4 vertices. But we did, in theory, know how those worked. So they were still able to get that to match up. And so then they made a video of me tossing this up in the air. So this is the same thing. That's the way it should fold, okay? And this is, and then this
Open
is
it up.
Folding it into not the right shape. This is like a corrugation configuration. So then, well, let's just watch what happens.
You can call it. Yeah. All right, 3, 2, 1, go.
Okay, here we go.
It folds.
Yeah, so there's a little bit of a delay there. But again, this doesn't work perfectly. There are some configurations you can torque it into where it'll fall into a well in the configuration space and not be able to get out of. But it also worked very perfectly in other situations. So there's more work to be done with this stuff. This this model is a theoretical model. It ignores a lot of things like friction, weight of the materials, gravity, and stuff. But and it sometimes, especially for bigger crease patterns, doesn't always work. But we're wondering if we can improve it. And this is something that I want to continue to work with Tomohiro and my students about. But there we go. This is the paper I wrote with Tomohiro Tachi. If you want to look it up, self-foldability of rigid origami. I think you can find it online. And yeah, that's a deep dive into one area of origami math that I think is exciting. So thanks. And again, if people have any questions, grab a mic. Yeah.
So Tom, those mode spaces, if you did all 4 dimensions, they would be the same curves, right, in 4-dimensional space?
What do you mean?
The original, the very first graph that you drew, those curves, those were projections down.
Yes.
So, but if you had them in 4 dimensions, would they be the same curves and it's just a rotation?
Yeah. I want to, in the example I gave, where the angles are 4590, 13590, they are. Because of the 90, because you have these two 90-degree angle creases here. But if you make it arbitrary for like alpha and beta, they're not.
Okay.
And that's what I tried to illustrate in some of those pictures where mode 2 looked like it had a bigger curve than mode 1. That's what I was trying to illustrate there. But yeah, in this case, they are perfectly symmetric. Mm-hmm. Any other questions?
I could see, like, with bigger shapes, there might be something about weight affecting the springs. Did you take that into consideration?
No, we weren't taking weight into consideration at all. So it's actually kind of interesting. So I did this work, I created this self-folding model with Tomohiro Tachi in the fall of 2015 when I was on sabbatical, and I was lucky enough to be able to go to Tokyo and hung out with Tomohiro for 5 weeks. Since then, some other physicists have tried to take this model and expand it or do other things with it. And I'm not even sure if any of their models actually use gravity either. Gravity is, because the thing is that if you start wanting to take gravity into consideration, then you have to consider how heavy are your materials relative to the force of your springs, and the size matters a lot. So what these other physicists are doing more with is they're trying to say, like, is there any way to avoid like this problem that we had when we put two of these vertices together? Can we avoid them by biasing the vertices a little bit in some other way? Is there another thing we can do other than just putting springs on hinges to help push in the right directions? That's been what most of the subsequent work has been on, but I know Tomohiro has ideas of like how to incorporate things like weight and gravity, and so I'm looking forward to see what we can do with that. But currently, no, it doesn't take that into consideration. Anything else? Yeah.
So the configuration spaces form manifolds. Are they? It feels to me like they should always be smooth. Is that the case, or? Yes.
Oh, wait. Yeah. So one part of this picture you're not seeing is that all those pictures I drew of the configuration curves, base curves, were for these like degree 4 vertices, or the symmetric case of that degree 6 vertices, in which case it's a 1 degree of freedom system and you get just these curves. If I was to look at the full configuration space of this degree 6 vertex, this has, 3 degrees of freedom. And so that would be an actual manifold, like a surface. But yeah, it should be smooth because as I move these around, I'm never hitting like a sharp corner or a singularity. I was hesitating because there are some, I don't know, because I was thinking of something else. So yeah, no, these are smooth manifolds, except at the origin. It kind of fails to be a manifold, because that's where your either curves or surfaces are intersecting at some singular point. And that point can look kind of weird. And strangely enough, there are people in algebraic geometry, like there's a great paper from the 90s called Hodge Theory and the Art of Origami. You're like, what? And all these two guys literally were like using origami as an example of, oh, look, cool configuration spaces. Can we prove something about the singular point at the origin? And they proved that locally around the origin, no matter what degree of your vertex, if it's a single vertex, it'll around the origin, it'll basically be a quadratic. Its tangent space will be quadratic. And that's nice. It doesn't help the engineers so much because there's not enough detail there. That's why we need like the equations and stuff to really figure out like what springs do we need. But yeah. Yeah, go ahead.
Just more of a speculative question, but
Okay.
I'm just thinking what the essential needs for flatness are, because of course you have flexible polyhedra and things, and presumably in that case the rotation matrix product would not be the identity. And
yes.
So obviously that's going to be different, but is there anything reasonable there, like some approach to Bellows conjecture-like things? For those who don't know, that means that flexible polyhedra can't change their volume or even now den invariant under these folds.
Yeah. If you were to try the Bellows theorem is wonderful. But that's if you have an enclosed surface that is polyhedral like this. Like if you were to make an origami model that wasn't just a flat bounded piece of paper, but actually enclosed a whole sphere of volume, and didn't have gaps between the creases like these, so it was like compressed, you wouldn't be able to flex it. You couldn't change its volume. So we get away with that. We don't have to worry about the Bellows thing here because these are not enclosing a volume, but there are other rigid constraints that exist. And some of it you can actually see just from the equations that I showed in this talk. But like, for example, this square twist, although let me get the actual crease pattern back. Here's the square twist. Notice in the square twist, the center square, I have 2 mountains at the top and 2 valleys at the bottom. The thick lines are mountains, the thin ones are valleys. If instead I wanted to make all mountains along that inner square, it would not be rigidly foldable. I could not do that with this. There's no way for me, I mean, the springs would make it really difficult here, but there's no way for me to have all mountains on this inner square and have these panels still be rigid. You can't do it. The reason for that is because remember how we saw how some of these creases fold faster than others? You know, like in particular, the ones, if all of these are mode 1, which maybe they are, I think, or I can view them that way anyway, because this has some symmetry to it, that's nice. Then like in this vertex, these opposite valleys would fold faster than these opposite mountain valley pairs here. And if you have all mountains going around here, then there's too much symmetry, and you end up having this crease has to fold faster than this one has to fold faster than that one, this one has to fold faster than that one, this one has to, and you get an inequality of their speeds in a loop, and that doesn't work. You can't do that with rigid folding. So there are various loop conditions that you can make that address exactly what you were talking about. But it's still difficult. With some other people, like this guy I mentioned before, Eric Demain at MIT, and a gaggle of other people who all worked on this problem, we were able to prove 5 years ago that looking at a crease pattern and determining can we rigidly fold it is NP hard. So it's difficult to just always tell, is there some way I can do the mountains and valleys to make this rigidly fold? That's hard. That's a computationally difficult problem, provably so, it turns out. Any other questions? Okay, well, thank you again. And I think, Sunil is running up here to, okay, yeah.
Thank you, everybody, for attending. That room over there where you left your stuff is still available. You can hang out for a while if you need to, or if you want to. And I don't think we've erased any of the words in case any of those problems you're working on is still interesting, and so I just hang out for a bit.
This ends our proceedings for today.
Right, in case I can't say it another time, please accept our gratitude for coming out to St. John's and St. John's. And thank you, Tom, again for the hands-on origami yesterday, and for all of you for attending that. Thank you so much.